Okay, so the second part of this lecture is on confidence intervals. And of course, we're going to talk a little bit more on bias, something that you have to do in your lab 4. So we'll get into it. Okay, so we're going to get into the confidence intervals in this lecture, and we will learn what we use them for, and then the procedure, how to do it, how to use the formula, how to work the problems, make a decision, and also how to be able to use the confidence intervals to make decisions, okay, or recommendations. Then we will take a look at how the size and the standard deviations of your sample impacts your confidence intervals. We use confidence interval in industry. We usually use it to estimate the average dimension of a large quantity of parts. Okay, parts are very important in our field. We measure them. We measure a very small sample from a large quantity. Okay, so you have a large quantity, and of course on a paper we call a data set, and then we're going to measure a sample out of that large quantity. So now you know this is population and that is sample, yeah. And we'll be using the confidence intervals to estimate the average, okay, dimension of these parts. So why are we using the sample is because of the cost. Yeah, if you sample the entire thing, it takes a long time, it costs a lot. So if we sample a data set out of a population, so that small sample reduces the cost of sampling. But of course, your error, is going to go up. So that's what it's saying, but increases the risk of an error in estimation. But relatively good size of sample is going to cover, this error up a little bit. Even though with the error we do it, so it's because it saves us a lot, and also we can still use these as sample data to represent the entire population. So we do that, So confidence interval, I have already explained that to you. It is an interval, So therefore, so let's just say like it is an interval. So you're gonna have a value in between that, okay, upper and a lower interval. So in that range of values, you're gonna have a real average is going between this and this maximum and then the minimum, value. So the probability of finding the real average between this two upper and lower, okay, value, which is your range here, is very high, so therefore we're very confident, let's say about 90%, 95%, 99% we're confident that the true average is going to be in between, all right, these two limits, okay. So that's what the confidence levels is about. Of course, we still have the risk of being wrong because we are dealing with a sample, but then this range or the level or this intervals, confidence intervals, definitely give us the estimate of that average, and definitely that average, the true average, is gonna be right in that range, okay. So these are guaranteed, so therefore we still use this method, in the industry because it is a reliable method. This is kind of like an example of what confidence interval is. So this is just a typical example. So we have Boss and Fred. Boss, all right, Boss said, Fred, I heard you measured a sample of 20,000 parts we made yesterday. So what did you produce for the average length of the whole batch? So Fred said, well, I am about 95% confident, that the average, the actual average of the whole batch is somewhere between 103.2 millimeter to 103.8 millimeter. See, like how we answer, we didn't give, we usually don't give the exact, right, average length of back to people who are asking, the value out of it, we always give a range like this, okay? So it means that I have about 5% error that it couldn't be in that range, but I'm quite sure 95%, right? Your average length is going to be between this and this. So here is your extreme, and here is your extreme, yeah? So this is your 103.2 is your lower, 103.8 is your upper limit, and your true average is in between them. Yes, oh, why the range? Why can't you give me a single number? Yeah, so the boss is asking you the absolute number of the average length. So Fred said, I can only give you a single number if I measure every part. And you said that was too costly, yeah? And you said you could accept no more than a 5% chance of being wrong. So I use a 95% confidence level, yeah? So this is how we deal with the everyday, yeah? So real life situation at the industries. Okay, so here, so notice Fred did not give or provide a single number as estimate. He provided a range, so 103.2 millimeter to 103.8 millimeter, yeah, as his estimate of the average of the whole batch. And Fred did not say the average is in that range. He said he is 95% confident that the real average is in that range, but that there is a 5% chance that that real average is not in that range. Okay? Yeah, meaning like it could be higher or lower. So that's the best Fred can do because the boss only let Fred measure a very small sample of the larger batch of the parts. Yeah, we don't get to every part in the whole batch because it costs us a lot to do that time, right? Because your employee salary or your employee wages depends on the time. So if you spend that much of time measuring each one of them to just get the average, it's going to cost you a lot, right? So we don't want to do that. Okay, so mathematically and graphically, we can be able to look at that. So here is your lower, confidence limit, 103.2, upper, 103.8. So our unit here in this example is millimeters, yeah? So that is your confidence interval because it gives you a range from here all the way to there, yeah? And on this side, you have about 2.5% chance the real average is going to be here, or 2.5% chance the real average is going to be here, but you have 95% chance that the real average is going to be in here, yeah? So I think you can be able to graphically see what's going on. You can be able to see this range very, very clearly. You can be able to see the error that you could make, yeah, out of that 5% offer value, 5%, which is 0.05, okay, in decimal value. So that error is going to be here and here, but the rest, 95% probability, you could get the real average length right here, from here all the way to here somewhere, yeah, in there. Well, that's a pretty good estimate. All right, let's get into the second example. Let's say we are making thousands, yeah, of commemorative gold coins, and we want to know the average weight of the coins because the gold is expensive, but we can't shortchange our customers either. So we could weigh them all, but this would take time and also cost, right? A lot. So we need a shortcut. So instead, we're going to just weigh a sample of them and then estimate the average or mean weight out of it, yeah? Since we're not weighing all of them, the range, so we produce, this is kind of weird. Okay, so I think the comma gotta be here, yeah? And here, yeah, this will do it. Okay, so since we're not weighing all of them, the range we produce, okay? The range that we produce is that. Okay, so the range that we produce is not going to be the real average or mean weight, right, of the whole population or batch of coins. It's going to be just an estimate, yeah? Why it is an estimate is because we sample a portion of the data out of that population data. We're not doing all of them, yeah, in that population. So therefore, we would just say it is an estimate. So we need a method to describe how close we think we are to the real average and how confident we are that the range we calculate is meaningful, okay? I'm just going to put that into here, so it's kind of better that way. Okay. So now you know the confidence, yeah? We have an estimated average. It's going to depend on how we sample and how we analyze the data, okay? So sampling method is very important because the sample you choose got to represent the entire population, yeah? So bad sampling is going to cause a really bad estimate. So sampling when not analyzing is costly, but so is gold. So we need a sampling strategy. So this is what we call sampling method. Yeah, that is cost effective, but it's got to be reliable. If your sample method is not reliable, your estimate is going to be not good. Yeah, cannot be able to represent the entire population. Then of course in lab 4 we will be using the T status students on T table. So that was introduced in 1905 by this guy, yeah, William Seeley Gossett, and he's a chemist actually and working for the Guinness brewery in Dublin, Ireland. So student was his pen name, yeah. So therefore we call that table students table. Gossett he had been hired owing to a clot, the Guinness policy of recruiting the best graduates from Oxford and Cambridge to apply the biochemistry and statistics to Guinness industry processes. So he devised a t-test as an economical way to monitor the quality of stout. Okay, so anyway, that's just a little bit of a history on your tea table. You don't have to memorize all of it. Okay, I'm not going to ask any of that. So at that time, so your industry was using oversimplified assumptions about the probability distribution when making sampling plans, and results were not very accurate. Yeah, so this is the reason why we have to use this T table. So he developed improved methods and he developed understandings of these sampling statistics with much better results, and it was then used at Guinness. Okay, so the t-test work was submitted to and accepted in that journal, something called the Biometrica, and then published in 1908. So the company policy at Guinness forbade its chemists from publishing their findings. So he published his statistical work under the pseudonym called student. Yeah. So see the student's T distribution for detailed history of this pseudonym, so which is not to be confused with the literate term student. Okay, this is just a cover anyway. So he had so they had a policy of allowing the technical style leave for study, and it's called a study leave. Yeah, sometimes professors also have a sabbatical study leave, so which Gossett used during the first 2 terms of the 1906 and 1908 academic year. And Professor Carl Pearson's biometric laboratory at the University College in London. So Gossett's identity was then known to fellow statisticians and to editor-in-chief Carl Pearson. So anyway, these are just for you to know a little bit about this on T distribution table history. So we're going to use the student's T table or statistics, meaning it's just numbers of table and then your confidence level to describe how good we think our estimate is. And this is a standard method that has been around since 1908. So first, we're going to randomly pick several groups of coins from the batch. So here are our samples, and say like 4 groups, 1, 2, 3, 4. Of 5 coins, so each group has 5 coins. We pick it out of that population data. So this is our sample data. Of course, we have mean weights and 4 stacks of 5 coins, and then we have our grand mean, which is, when you look at it, this is an X bar, so it represents the sample mean, and then of course the little s is going to represent the sample standard deviation. And to save the time, we're going to weight the 5 coins, coins 5 at a time, and calculate the average weight. So here is my first, average, second, third, and then fourth for each of the 4 groups. That's providing you have 5 average weights right now. First, second, third, and then fourth. Now we found the average of the averages. So this is your first average, second, third, fourth, and then we're going to get the entire average out of that averages. So first we average this, and that, and then we're going to average that 5 averages out of it. Yeah, so I am going to write that down for you. Yeah, so you have a mean 1, and then you have your mean 2. Of course, you can do like this, little x, yeah, one group, and then second group, and then the third group. Yeah, and then of course this is going to be your fourth group like this. Yes, and then you're going to get another average. Yeah, so now sum it up, divide it by 4, and you're going to get the grand mean, which is the big X bar, yeah, out of it. Okay, so that's what we're doing right here. So now we found the average of the averages. We call this the average of the averages, yeah, and the standard deviation of the averages. So we use the average of the averages, which is the grand mean right here, to estimate the interval we say the real average is likely to fall into. Okay, so now you kind of get it by looking at graphical, yeah, representation here. Okay, so what is our confidence in this estimate? Yeah, so we pick are given a confidence level, let's say like 90%, 95%, 99%. Yeah, we can pick out of it one of them, and then we're going to use a student T table, and then we're going to calculate the upper and lower confidence limits. So we call the range, and between these two limits, the confidence interval. Yeah, because we gotta use a T table is because when we calculate the confidence intervals, if you remember, the confidence interval formula, yeah, contains a little T value, which we can be able to get it with the degree of freedom n minus 1, and then their confidence level. Yeah. We're going to say like, oh, we are 90% confident after, of course, calculating the confidence interval. We'll say like 90% confidence if you chose 90%. 90% mean you have like a 10% error, yeah? But that our actual population mean weight is somewhere between these two limits. Okay, so that's all about our confidence interval. So this is not strictly correct, because of what we should say is that using this method 90% of the time, the real mean will be between these limits, but 10% of the time it won't be. So this is the real interpretation of the confidence interval. Of course, we don't really say, we usually just say like we're 90% confidence, yeah, that the mean is going to be in that range, like that. But formally is this, the way that you should be saying is like this. So if the desired target weight is not between these limits, then we are pretty sure our clients are averaging either too heavy, yeah, or too light. So this is when you can make errors, so giving away the goal or cheating the customer if that's too light. Yeah, if your mean is not going to fall into that 90%. So we say that the margin of the error is plus and minus half the confidence interval. Okay, now we're going to see another example here. So the boss say, oh yeah, so let's use 95% confidence level to determine whether we are on target, giving away goal, or cheating the customer, and to adjust the average if we're not on target. So the target weight for the gold coin here in this example is 5.6 grams. Yeah, so here this is your target. So the result of the weighing the coin results in the X bar, the mean, is going to be 5.7 gram. Okay, this is where our X bar is, which is your mean. Okay, and then your students stat is procedure we calculated, and we're going to get our lower confidence level, and that is going to be 5.57, your LCL, lower limit, yeah, and then your upper limit is 5.83. So that's come from your confidence interval calculations, yeah. So we have a target, we have our mean, we have lower and upper limits right in there. Okay, so these are the margin error. Your confidence interval is 5.83 all the way to 5.57 gram, yeah. So if you subtract it, you're going to get a range, because that's your max and the minimum, yeah. So your range is 0.26 gram. And your upper limit, your lower limit, target, and your X bar, okay. So we would typically say that we are 95% certain that the mean coin weight, all right, of the whole batch is going to be between, all right, that two. from here all the way to here, but we don't actually talk about the mean of the sample. Yeah. So anyway, so from here, actually from here to here, yeah, the range is. So in reality, what this means is that if we repeat this test right over and over, we're gonna get like 90% out of 100. Okay, mean will be between these limits. Yeah, we will always have see that our mean is right in between that two limits. Of course, our target is right there, but our mean is there. So even though the target is right here, still your mean is within that range, and your target is also within that range. See that? Of course, we have a little bit of a deviation, yeah, your mean from your target, but it's not much of a difference. Yeah, it's about like 0.1%, so it is acceptable. Okay, I think you kind of get the idea of that. Yeah, this is what the company desired, but in reality, we can't deal with the entire batch. Yeah, every part of it. So we take a sample out of it. We calculate the confidence interval with some percentage of error, very small amount of error, yeah, and we got a range, okay, with the upper and the lower limit, and your mean, okay, of your data set from your sample is going to be in between that, yeah, along with your target, yeah. The target and your mean, okay, it's not the same. Sometimes they will overlap and sometimes not. If they overlap, that's pretty good. And if they don't have like a distance like that, have some deviation, yeah, from the target, that's okay, as long as your mean, okay, from your sample is still in between that. So what we truly want for the entire batch is 5.6, but our sample set, yeah, the mean is still within that range, close to that target of 5.7. So, and that just for the sample. So therefore, the real, yeah, the true mean got to be close to that 5.6 if we do, yeah, actually measure every part in the whole batch. Okay, so this is our estimate, and it's a pretty good estimate. Okay, so because we have only like 5%, yeah, error, meaning like your mean is not going to be in this range out of it, and that can only happen 5%, yeah, out of 100. Okay, so another graphical, interpretation that you can be able to see that's just a tilted, graph, but it's the same thing. So you can see right here, your sample mean is here, your upper limit, your lower limit is here, your error can be here in this, area. So your 95% confidence, that your mean is going to be right in between the two limits is here, this area. Of course, graphically we call this area, yeah, that's the area and that's the area because it is under this little curve right there, which looks like a normal curve, yeah, because it is a bell shape. Majority of the data set display a graph like this, and we call that the normal distribution because they usually come on this type of shape, okay, a bell shape, and sometimes it's gonna come a weird shape, but we're gonna call it that's not a normal distribution, but most of the time, okay, almost all of the data set produces this type of curve, okay. Anyways, your upper limit, lower limit, you get this from calculating the confidence interval. So this is your interval, that is your target, and this is your sample mean, yeah. Alright, so the next one here. Okay, so here are the possible outcomes. So if we have like 95% confidence interval, yeah, we have to think about if we need to adjust the average or not, because our average is right here, and here is lower and the upper, and your target is outside of your interval. Here in this case, 95% confidence level, and then we think again, oh, should we adjust the average? Yeah, because your lower, your upper, your target is inside of the interval. Yeah, and the next case, a 95% confidence interval, and then we look at it and we think, should we adjust the average? So here is your lower and the upper, and here is your target is outside of it. Okay, so you can have like 3 different scenarios. So I'm gonna go back to the one slide up. Yeah, so these are error area. So you have a first area about 0.025. This one is 0.025. So it's like about 2.5% and together that would make like 5% error, up here and down here in the middle, so we have a up here and down here and then the middle. So our target is out, our target is right in there, our target is down here. And you don't pay attention to your x bar, okay, because x bar represents the sample. But of course, we're using that estimate to represent the entire population, but when we determine what's important is this interval, okay? So your LCL and the UCL, confidence level right here, upper and lower confidence level is very important, okay? And of course, we're looking at the target, the target, right? Because that's the desired, what we want it to be, so So this is pretty good, and then of course if you get this you need to adjust, and you don't need to adjust because your target is inside, So now I will write that down for you, So this one you have to adjust. Confidence interval, right, entirely above your target. Here you need to adjust. Your confidence interval is entirely below the target, I'll make it a little bit easier for you to read. And this one is pretty good, because the target is inside of your confidence interval, So we don't have to adjust the weights. Okay, so one common mistake students make is they have a confusion between the x bar and the target. Target is what's important. Target is the one that we want, right, to use to decide. X bar as a sample mean, okay, it has nothing to do with the desired value, okay. So even if your x bar is inside of the confidence interval, that's just representing your sample, right? Meaning like your stuff 95% confidence doesn't include your target, okay, weight. Here in this case is grams. So anyway, so your target data, So you got to be very, very careful when you make a decision what you're looking at, okay? Now I am gonna get into a little bit about your lab 4, what we have to do. So the optic side, I think that's a lab 5, but our side, MET, mechanical technology, you aren't gonna do the lab 4, we counted 4. So the lab 4 purpose is to check, to check the bias in your operator system, which is your measurement system. So you have expert measure parts using a highly calibrated and accurate instruments, and then you have your operator, that's you, measure the same parts, your gauges, whatever you normally use to make the measurement, the instrument in our labs in your box, and then you will compare the difference between the measurements. So that's what we're going to do in our measurement system. So in lab 4 you're going to measure dowels. So this is just a cylindrical rods, and you're going to see them in the lab. So we have 4 different measurements. We're going to do 4 different measurements. So these are your samples, by the way. So then you will compare your measurements to those previously made by an expert. So you take. So this I will of course provide you the tables. So I have already provided you the lab, right? And you have about 8 pages, I think. You're gonna see all the way down. So there's an expert data, taken with tables for your dowels. So that's what you will be using for that, data. So you take the difference between your measurements and then the known measurements. We're going to treat these differences like any other data and then calculate the sample mean, which is your x bar, and your sample standard deviation, your S, and then the upper confidence limit, your UCL, and lower confidence limit, your LCL. And then you're going to decide whether we think there is bias or not. Bias means like if you aren't doing right with your data, your measurement data, and we're going to look at against the expert data. So in the previous example, there was a target, and you have to decide what is the target in this case, okay, in your lab, of course, because without the target it would be very difficult for you to decide your confidence interval is okay or not okay, or needs adjustment or not. Okay, and then of course in this case we hope there's no bias, so the target is 0. Again, we're not doing the mean of your dowels measurement. We are our target is bias, not the measurement of your dowels. Okay, so our target is bias, and of course we don't want any bias, so therefore our target is 0. So after we calculate the confidence limits, we're gonna just look to see, all right, that confidence limits include your 0. So on the limit positive, one limit is positive and the other limit is a negative. I'm saying on it because actually there's this got to be 1. So one limit is positive and one limit is a negative. So if one limit is positive and the other one is negative, we say we are 95% confident that there is no bias. And if both limits are positive, or both negative, we say we're 95% confident that there is bias in the system. So graphically, this is how you think. Make sure you don't pay so much attention on your x bar, because that's just a simple mean. We're gonna pay attention your limits. When you do your decision. So this is no bias. Why? Because we're gonna think like it's one limit positive and one limit negative. Okay, and then we're gonna think about whether your target 0 is in there. If your 0 is inside of your confidence interval range, then yes, then we say there is no bias in the system. But if your 0 is outside of it, no, they are both positive or both negative, then then we're gonna say there is bias in the system. Okay, so meaning your 0 is not in that limit. If your 0 is not in the limit, your UCL and LCL, and is outside of it, okay, then we're gonna say there is bias in the system. Okay, so this is how we're thinking. So here is your LCL, UCL, your 0 inside, your 0 outside, outside, outside. Okay, and here is your 0 outside, inside. Your 0 inside, your 0 is inside, and then your 0 is inside. Okay, so now you can take a look at it. So here, look at this. Your 0 is inside, no bias. Okay, here look at this. Your 0 outside, so there is bias. 0 outside, there is bias. 0 is way outside, so there is bias. 0 is outside upper, there's bias. 0 is inside, no bias. 0 is inside, so no bias. And 0 is inside, no bias. And 0 is inside of the confidence intervals. So therefore there's no bias. Okay, so that's what you have to do in your lab. And I think based on extensive experience, students are going to struggle the averages. So first you're going to think like which average what I'm going to do. So you're going to have to do a different average group, and then you're going to have to get another average on top of these different averages. Okay, so you're going to get a grand average. So you're going to use that average, but don't use that average and decide. You have to understand that you are deciding with the target. Okay, and we don't want the bias. Some bias got to be 0, so your value got to be 0. So if you're getting something else, then you have bias, and that's something else, which is your 0, target 0, got to be inside of your confidence interval. And this is how we're making the decision. So based on the teaching, right, experience, I usually see that the students are using the sample mean as a target. Sample mean is not your target. Okay, target is explicitly telling you 0. All right, because we do not want bias in measurement. So therefore your target is 0, and that 0 got to be inside of your confidence interval for you not to have the bias. Okay, all right, so that's it for this week.